Right. Welcome, everyone. Thank you for joining us for our 13th Fluorescent Friday event. My name is Dr. Lina Cardenas, and I'll be your host today. I'm an assistant professor at the School of Design at the Pontificia Universidad Católica de Chile. Before we begin, I'd like to ask you to keep your camera off and your mic muted during the event. Thanks. Please use the chat box to tell us who you are, where you're from, and your affiliation with a university, company, or organization. The Inter-Society Color Council created Fluorescent Fridays as a global platform for university students from all disciplines to network with color professionals and fellow students, and to share state-of-the-art resources about color's role in our lives and applications in the world. If you're interested in getting involved, please check out our website to join our mailing list and learn about the benefits of becoming members. We welcome you to join us. Today's event celebrates Halloween and Day of the Dead, and is titled Saving the Planet Through Optics Education. During the program, we will hear from Dr. Jennifer Kruschwitz and 3 of her students, alias agents M, J, and D, from the Institute of Optics at the University of Rochester. They will introduce the audience to the abundance of optical phenomena that results in or utilize color. The agents will wrangle with topics such as polarization, color mixing, refraction, and diffraction in a way that will illuminate the mind and dazzle the senses. Each topic will be presented with a visual experiment, and the agents share a list of equipment so that inquiring minds can replicate each of their own. No math skills are required for attendance, only curious individuals who want to know more about optics and color. The timeline is about 60 minutes. After the presentations, there will be a 10-minute Q&A with the audience. During presentations, we encourage you to type, the typers can address the questions and they'll answer them at the end. Our first speaker is Dr. K, aka Dr. Jennifer Kruschwitz. She's an associate professor of optics at the University of Rochester and a senior scientist at the Laboratory for Laser Energetics. She received her BS and MS in optics from the University of Rochester and her PhD in color science from Rochester Institute of Technology. She authored the field guide of colorimetry and fundamental color modeling through SPIE Press in 2018. She teaches courses in wave optics, optical interference coding design, and color technology. With her 35 plus years of optical thin film coding design and color experience, she supports research in hyperspectral imaging and color calibration target design. This year, she's featured in SPIE's 20th edition of Women in Optics. She's the president-elect for the Inter-Society Color Council and will be the president in 2025. Jen, it's an honor to have you here. Welcome to Fluorescent Fridays.
Thank you, Lina. So let me share. Okay, so I'm going to be giving a presentation about the University of Rochester's Institute of Optics. So this is our larger building This building is referred to as the Gergen Biomedical Optics Building, and it was built in the early 2000s. All right, so where is the University of Rochester? Where is Rochester, New York? Rochester, New York is located right where this arrow is, and it's on the edge of Lake Ontario. Now, Rochester is halfway between the city of Buffalo and the city of Syracuse, even though we don't get as much snow as Buffalo or Syracuse. And we are about a 6-hour drive from Boston, a 6-hour drive from New York City, and we are referred to as Western New York and not upstate New York. So about the Institute of Optics. It was established in 1929 at the University of Rochester. It's an academic institute. So we offer bachelor's degrees and master's degrees and PhD degrees. So the bachelor's degrees are in optics as an applied science and optical engineering. Our master's and PhD degrees are in optics. We are also a research center. So one of the major roles that the Institute played at the very beginning of the last century is that the US got most of their optics from Germany. So the Institute of Optics played a central role during World War II in order to support optics design and manufacturing for the US during that time. We have continuous and close partnerships with optics industries throughout the United States, and our current enrollment for undergraduate and grad students is about 350 students. Now, this is one of the newspaper articles that came out when the university decided to add the department to teach optics, and we had Kodak. Kodak is located in Rochester. Bausch & Lomb is located in Rochester. Xerox is also located in Rochester, but at that time in 1929, Kodak scientists and Bausch & Lomb scientists specialists were going to help form this new institute. So the impact that the Institute of Optics has had, we are the very first program in optics in the US.
And coffee.
And so another thing about, we have alumni and faculty that have started greater than 200 companies in the US. And then about 40 of our alumni and faculty have been presidents of very large professional societies, such as the OSA, which is now called Optica, SPIE, the APS, and there'll be one next year that will be president of the ISCC, which is me. Now, out of the 12 most cited physics books in the world, 3 out of the 12 were written by optics faculty here at the University of Rochester. We also have a Nobel Prize winner. Dr. Donna Strickland, she graduated with her PhD from the University of Rochester, and she worked over at the Laboratory for Laser Energetics. And just a little bit of trivia on her Nobel Prize in physics. She won the Nobel Prize for a paper that she wrote when she was a third-year PhD student. It was her very first paper that she wrote, and that's the topic of that paper was why she won the Nobel Prize in physics, and that's pretty impressive. And so for graduate students that are out there, you too could write a paper that could win you a Nobel Prize. So at the Institute of Optics, we have some optics research centers. We have the Center for Coherence and Quantum Optics. We have the Center for Visual Science. We have the Center for Freeform Optics, which is a new way to design lenses. And then we have the Robert Hopkins Center for Optical Design and Engineering. Now, one of the wonderful things that happens at the Institute of Optics is twice a year we have something called the Industrial Associates Program. And we just had our Industrial Associates, which we refer to as IA, just last week. And so representatives from about 60 plus companies, and they're not only in the United States, we have companies from China, we have companies from Germany, we have companies from all over the globe, come to Rochester twice a year, once in the fall and once in the spring. And it's a big event, and it's all day long, and talks are by faculty and company representatives and guests. Talks and posters are by our undergraduates and our graduate students. And the companies that come, they specifically want to meet our students. So they'll have interviews for internships or co-ops or jobs. And it's a huge event where we have lots of networking opportunities. And this year we had it in our convention center in Rochester. And the program is so big that maybe next year we'll have to have it in our Blue Cross Arena, where ice hockey games happen and concerts happen, because we've outgrown our space at the convention center. So I talked a little bit about the laboratory for laser energetics, where Dr. Donna Strickland worked as a graduate student, and she won the Nobel Prize in Physics. I am a senior scientist at LLE, and the laboratory for laser energetics is trying to find new energy sources using high energy lasers. So they are investigating inertial confinement fusion, or ICF. And they've done over 33,000 experiments since 1996. And we lovingly refer to it as the Laser Lab. They work with Lawrence Livermore National Laboratories. And there's a laboratory in France, a CEAS, that also is working with collaboration with LLE. And they all are, it's a unified activity where they're looking to create fusion, laser fusion. And just as an aside, 2 years ago, Lawrence Livermore National Labs achieved ignition. So that was a really big announcement that happened. All right, so what about our graduate programs at the Institute of Optics? Our total enrollment is greater than 180 graduate students, and we're growing every year. So in our PhD program, students can study imaging, they can study human vision, they can study lens design and lasers and photonics. And we have a new augmented virtual reality group. For the master's students, we have an in-person master's program. And then we have a brand new program that started during the fall of 2020, but it wasn't because of the pandemic. This program, we had already put it together in 2019. It's called the Hybrid Optics Master's Education Program, or the HOME program. And this invites students from all over the United States, Canada, Mexico, to be able to take classes at the University of Rochester remotely. And there is no differentiation between the in-person master's degree and the home master's degree, because the home students will come to campus for 3 weeks and do an alignment intensive laboratory. And that's why they share the same master's degree. We also have a co-op program for master's students as well. All right, so 4 miles down the road is our university neighbor, which is Rochester Institute of Technology, which is where I got my my PhD degree in color science back in 2015. And another thing about the Rochester Institute of Technology, RIT, is that we're going to be hosting, the ISCC is going to be hosting our conference called Color Impact 2025. And the theme of that is color as communication. And it's going to be next June, June 16th through 18th. And there are going to be short courses, technical talks, and we're going to have a lot of events that will be going on for those 3 days. And so I let the audience know that we're going to be offering a short course on the experiments that you're going to be seeing in this presentation today. All right, so it's time to move on to our agents, and I'm going to be introducing them. The first agent, his name is Demetrious Dowdell, And Demetrious is a fourth-year PhD student at the Institute of Optics. His research focuses on holographic metrology. He is from Rochester, New York, and also completed his undergraduate degree at the Institute of Optics. As a sophomore, he became a coveted Ronald McNair Scholar, where he was able to start optics research and preparation for graduate school. Demetrious is a GEM affiliate and is currently a Pathways intern at Goddard Space Flight Center. He aspires to join a metrology group upon graduation from the doctoral program. He is currently the science outreach leader for the Institute of Optics, a tutor for graduate geometrical optics, and a teaching assistant for an introductory optics course for first-year students. During his free time, he enjoys rollerblading, climbing, listening to music, and helping others in optics. So our next agent is Agent Megan Fallon. Megan is currently pursuing her master's degree in optics at the University of Rochester. She just received her bachelor's in optical engineering in May of 2024, where she was inducted as a member of Phi Beta Kappa Academic Honor Society. Megan was also awarded the Donald M. Barnard Prize from the Hagem School of Engineering for personal character and achievement. She is interested in lens design, optical fabrication, and optical interference coatings. Currently, she is researching generating starting points for zoom lens designs. And beyond optics, Megan enjoys knitting and juggling, and she is fantastic at both of those. All right, so our last agent is Jayvyn Dennis. And Jayvyn is an undergraduate third year, so a junior, and he's from Central New Jersey and an optical engineering major. He's currently working for 2 different professors at the university on both electrical circuits and photonic integrated circuits research. He was presented with the Fujimura Prize in Optics as a sophomore for academic excellence, research, and campus citizenship. Jayvyn works with Demetrious on his team on kindergarten through 12th grade outreach at the University of Rochester, and in his free time enjoys playing a series of advanced computer video games. So with that, I'm going to stop sharing, and agents D, M, and J will start their presentation.
All right, hello everyone. I'm Agent M, but for the purposes of this presentation, you can all call me Megan. It's my civilian cover. So let's start with students in color. Oh, there we go. So for our itinerary, we're going to be talking about polarization, then color mixing, refraction, and finally diffraction. So firstly, let's talk about what polarization is. So polarization is a fundamental quality that describes light. One of the things that we're very familiar with is color. Obviously, everyone here is interested and related to color in some way. So polarization is essentially the directionality of that light. It could be traveling and how is it bouncing up and down. That light could all have the same wavelength, but fundamentally is different based on the orientation that it's traveling in. So for a little bit of a explanation on polarization, so initially light tends to be, we call it non-polarized when it's oscillating just randomly every which way, all the directions are sort of superimposed onto one another. And so we have this optical component that's known as a polarizer. And you can think of it like a one-way fence that only lets light wiggling in one direction to pass through it. So if we look at these top 2 pictures with the flashlight, and you can see there's randomly polarized light that's oscillating all of the ways, and then we add a polarizer, and it only lets light in the specific orientation through. So say we add a second polarizer in the same orientation, that light also goes through. So you could think of this in a more physical sense. Say that you have a friend and you're both holding one of either side of a rope and you line up fences. And if you have 2 fences that are both facing upwards and you start yanking the rope upwards, then once it gets to your friend, it'll still be moving up and down. So you'll be able to tell that that's the quality of that light. Say you take that second fence and you rotate it 90 degrees. So now you have an upwards fence and then a sideways fence. If you start moving the rope up and down, your friend's not going to be able to see any motion. So that's sort of the concept of what polarizers are doing to polarize light. And so it brings this concept of cross polarizers that they don't allow any light through. And so adding a second polarizer rotated in the opposite direction just blocks all of the light. So a really interesting way that this applies to color is you can actually use it to see material stress. And so the setup that we have here is that there's a light box that's just putting randomly polarized light like I described before, and laying on top of that is one polarizer. Then we place in an object that we're interested in seeing the stress of, something translucent ideally, and then we put another polarizer on top of there, and I'll play the video so you can see the effect. So this is before we place the second polarizer, we put the fork down and it just looks like a plastic fork. But then once we have the polarizer, you can see this really beautiful color effect. And you can see that the color is changing in different parts of the fork. And so when Demetrious pushes the tines, the stress that's within that plastic of the fork is physically changing the colors that we see. And you can see when you bend it that way, it's less stressed than when you did the tines because the colors didn't change as much. And so that obviously creates a really beautiful effect, but maybe you're wondering, why should I care about that? That's fair. So it's really good for observing material stress. And so, for example, this is a process that's actually used when you're manufacturing car windshields. When a material has a lot of stress in it, it's holding all of that sort of force so that if something, say, hit the window, then all of that stress would sort of come out flying into shattered glass, and you're in a car. You don't want the shattered glass on you. So you can look and use this method with the polarizer, and you can see, oh, that part of the windshield is really stressed. And then you can fix that by annealing. So you heat it up, the material, so it doesn't melt, but just enough that the molecules forming it will sort of settle into a more stable position. So then if a car accident does happen, the windshield doesn't shatter and go everywhere, it'll just crack. And so this is another cool thing that we put. So that is a little plastic molded shot glass. You can actually see this really beautiful cross pattern that comes with the stress. And it creates a really beautiful effect from just all of the colors, and as you rotate it, rotates around, and you can see the polarizer in that orientation, it's crossed 90 degrees, so the background doesn't allow any light through. And then when it's rotated, fully aligned, pretty much all the light comes through. So that is known as stress birefringence. And so wavelengths, the polarization of those change, and they are allowed through only for certain colors. So then you get this really cool color effect. And so this is just the inventory for that demo, if anyone would be interested in recreating it. So as the base, it's just a white light pad. That's something that you might get from Michael's if you're doing tracing or anything. And then 2 polarizers. And then pretty much anything that's injection molded plastic or clear will look really cool when you put it in between, and you get the color effect. So another interesting use for polarized light, because stress-induced polarization isn't the most applicable thing in your daily lives. So I'm going to do a quick aside and talk about depth perception, and I promise we'll get back to polarization. So when our eyes are viewing an object, our brain is really smart and it's able to figure out whether or not it's close or far. And the way that you do that is that your eye sees a different view of each object, and then your brain sees the 2 pictures, the one from your left eye and your right eye, and it goes, oh, I know how close that is. So if you want to just demonstrate that, you can place your finger about 6 inches from your nose and then just close one eye and close the other, and you notice you're fingers jumping around. Your brain processes all of that and you end up with depth perception. So 3D movies are essentially creating artificial depth perception. So you actually use two different cameras and they're slightly offset from each other, mimicking our eyes. And you then need some method to deliver so that the photo from the left camera goes only to your left eye and the photo from the right camera goes only to your right eye. So the way that this used to be done was using complementary colors in 3D glasses, covering some type of film. And when I was little, that was how 3D movies worked, and I didn't particularly enjoy them. They made me sick. The color rendering was really bad, and taking the glasses off gave me a headache. So it would be really great if there was some quality on light that we could filter that wasn't color so we could get an authentic color rendering experience. And that is where we go back to polarization. So since there have been so many technological developments, there are now these really cool projectors where they can actually project two different polarized views. So then the view for one eye is polarized 90 degrees to the other, and then the glasses just have opposite oriented polarizers. So then one eye completely gets one image and the other eye completely gets the other image. And then it looks 3D, but it's perfectly colored.
All right. So everyone, Agent Dowdell, but our civilian identity as we're going by is just Demetrious. So we've talked about how polarization can be wavelength dependent as well as the absence of some color in the demos that we were talking about. But what we'll get into is how we'll use colors for, say, some more fun demos. So what we have here is a additive color scheme. So what we'll have here is essentially our primaries, which is red, green, and blue. And if we combine these in any different amounts, then we can either get white, cyan, yellow, or magenta, as we can see in our picture here. So with this whole scheme here, what are we trying to do? What do we want? What is our aim for this here? So this is where we actually take these additive colors and take them in action. So we have a demo that was here on our left. This was provided by Monroe Community College, or MCC. And this is something that takes essentially these lights and shows how they will mix if you have equal amounts of all of these colors. But now we get to the point where, what if we block one of these colors here? So what if I put my hand in front of the green light or the red light or the blue light? And the pretty magical thing here that happens is that we will get a mixture of the other two colors that are present. So if I block the green light, then we will see the mixture of red and blue and vice versa. So now we get to subtractive colors. As we saw there, when we had the mixing of the other two, we could kind of see a hint of these colors here, but that was not used in that color system. So subtractive colors, which were the ones that we were seeing in the previous slide, when they're actually used in that system, is for dyes, paints, etc. And we can see that where we had all the colors combining to make white light, now in this case, we have it creating black. And we can see this when we get to the diffraction demo, when we have the paint on these, well, more so on these, I'd say lights, if you will. And we can kind of observe that when we're looking through a grading, which we'll talk about later. And for this here, just to show this again, all these parts were from Thor Labs, and this was provided by MCC. So it's relatively okay to buy, but you can just use a red, green, and blue LED, whichever you prefer, and you can essentially recreate this demo. So now we get into what happens with light when we have an interface. We are just talking about light mixing and having fun with that, but what happens if you say shine on a piece of glass? And that answer would be refraction. So we have light that's coming through, and it will essentially hit the surface and bend at an angle when it's going at a oblique angle or any random orientation with respect to the surface. And this also is something that can change with color. So this is essentially called dispersion. And this is a property of the material that when you shine a white light, each wavelength will experience a different angle of refraction. And this can be directly proven by, say, taking a lens and just experimenting with it, which is pretty fun for children to have. So This picture on the right is showing the final result of what happens with different wavelengths. But if I just showed you that picture and we took it as is, it's all right. So what we have here is essentially proof of that, is taking each color, shining it into a lens here, and marking the point of where it actually intersects with what we defined as our axis. So we defined a line that's in the center of the lens, and we marked roughly where each color went. And as you can see, as the wavelength starts to decrease, or as the colors change, our point is moving slowly to the left. Our last color, as we saw here, now we have the furthest point away. And then for our lovely blown up version, we have right here. So this shows truly that each of these points are going to a different location. And with the demo, all you truly need is we have a Tech Light kit. You can buy those, or you can have a laser block with any standard lens that you can find, whether it should be a positive lens in this situation, but each should work. And with that, we will go on to.
Hello, I'm Agent J. You can call me Jayvyn. So I'll be going over diffraction. So when light hits a very small gap in some material of differing shapes, it'll cause the light waves to spread out at different angles. So different wavelengths or colors will be sent off at a different angle. And that happens when we have these diffraction gratings, which are just films with very tiny gaps in them, and that causes the light to diffract. And then on the right, we have a phone camera with a diffraction grating placed on top of it, and that's what we use to get the pictures we'll be showing later. So here we have a white light bulb, and then when we put a diffraction grating up, it'll split it into different colors. So if you want, just put in the chat what colors you think the light will show. So here you can see that it's from red to dark purple. You can see the diffraction grating split up the light. So now we have a few different light bulbs that are coated with a glaze, and that causes the wavelengths that you don't see, the colors that you're not seeing, are absorbed into the glaze. So here we have a red light bulb, and then again, you can just put your guesses in the chat of what types of colors you think will show through the grating. So here you can see that only red is getting through. So the glaze is blocking out all the colors except for red, they're being absorbed. And now we have an orange light bulb. So what color do you think will get through the grating? So here you can see there's a little bit of red and then a little bit of green on the edge, and then they combine in the middle to form an orange color. And now we have a yellow. And here you can see that there's red and green on the edges, a little bit of orange on the left there, and then mostly yellow in the middle. And then a green light bulb. And then here we can see that the green gets split up into red, and then on the left, and then blue on the right, and then a little bit of purple in the bottom corner there. And here we have a dark blue light bulb. And that gets split into mostly green and then a little bit of purple on the right. And in the middle, they combine to that dark blue color. So these pictures were all taken using these rainbow peoples, which are gratings, and we'll have a link that you can buy them at later. But now we're using them to look through these, just a white dot on a screen. So on the left, you can see that it's red and a little bit of yellow on the outer edge, and then blue and cyan on the inner edge. And then here we have another picture just taken a little bit further away. And then you can see the colors spread out more. So here we have a few different colored dots and a few different shapes. Here's a yellow dot that forms green on the inner edge and then red on the outer. And then another picture from a little bit further away. And then a magenta dot, which ends up forming a red and purple combination for around each dot. And another picture a little bit further where you can see some green and then more of a blue on the inner side. And then here's just a compilation of stars. And then you can see that this has similar to the white dot, it has a similar color gradient to the white dot, but it's in a more interesting shape. So all of our demo inventory can be found here. The diffraction grading, the rainbow peepholes, and the bulbs are all here. So if you're interested in buying them, you can do that. But back off to Demetrious.
All right. So with that, we have our references for how we're getting everything. And then we'll start off by saying thank you so much for your time. And then if you have any questions, you can feel free to look into the light. That we'll say, ask if you have any questions.
So I'm Jean Hoskin, and I'm the moderator for the question and answer section. And while you are taking some time to put some questions in, I'm going to make an announcement and then also ask some questions that I have. First of all, the parts list, if you didn't get a screen capture of that information as it went through, we will be sending out a PDF of that information to everyone who is registered for this particular Fluorescent Fridays. So my question is related to, these are all fun, and I like to see all kinds of colors generated from different types of optical devices, but I want to know, what is the actual practical application of using some of this information that you've just shared with us? For example, for polarization, they used to sell polarized sunglasses. Is that still a thing? And why would you want to buy a pair of those?
Oh, Megan, are you going to answer that question?
Yeah, I can take that question. So essentially, polarization, sort of like we talked about how there's polarizers and they selectively allow certain orientation of light to pass through. So the reason that polarized sunglasses exist is the main thing that they'll explain to you in the optician's office is that reflections off of water, those all tend to have a specific polarization just due to the light from the sun is randomly polarized, but once it reflects down to the light and makes it back to your eyes, there's only a specific polarization that is known to opticians. And so they use that to determine the orientation of the polarizers. So for things like glare, the polarized sunglasses are able to reduce that without reducing all types of light. Because anytime that you're designing an optical device, there's certain standards that you have to be able to meet, particularly that you're able to still see all the things that you need to see. Like a really interesting one that I learned about when I had a friend who was concerned with some glasses designs is there's this very specific standard that you have to be able to see stoplights. That if you have sunglasses, you need to be able to see the red, the yellow, and the green lights, which actually there is a standard that is defines the specific wavelengths. And so, yeah, so polarizing sunglasses, they essentially are able to reduce glare. And so that's the practical purpose.
Yeah.
Is there one wavelength that is more damaging to the eye than another that you might want to filter out?
Absolutely, yeah. So one of the things is UV rays in particular. I mean, UV rays are just in general not good for us. I think I'm not as much of a visual scientist, but in addition to just wavelength, there's also one of the dangerous things to the eye is simply the amount of light. Like if there's just too much light that you're looking at, the way that our eyes see is that the lenses on our eyes are focusing light onto our retinas. So if you're looking at like it's why they say don't look at the sun directly, because that's a lot of light, and then that all filters down right onto your retina, and then you can get burned or you can get injured from that. So that is additionally a reason why wearing sunglasses is safer, is it reduces the actual amount of light.
So you talked about analyzing stress, and you said that wavelengths change only for certain colors when object is put under a certain amount of stress. So do certain colors relate to specific stress levels? Is there a correlation between the color that you see and the amount of stress that the object is under or the material is under?
So Jen might be able to speak a little bit better to this than I could, but so one of the things you might notice is that as you actually rotate the polarizer in the demo, the color changes. And so it's less the actual color itself, but more the amount of color changing in a specific area that would be an indicator of the stress.
Okay.
So for the areas that were mostly all one color, there's versus the areas that are quickly changing color, that sort of indicates that there is more stress in that area. And Jen, if you want to add anything to correct that, please feel free.
Yeah, so in the slide that they had the video of the little cup, and they had that cross, that's called the Maltese cross. And that's something that individuals will look for when they're after they're annealing the car windshield. They want to see a Maltese cross because that is an indicator that the stress has been annealed away. And so at the bottom of that cup, I don't remember, Megan, when you guys were taking that video, the cup had a crack in it, and that released the stress in the plastic cup, and that's why it had that Maltese cross at the bottom. So anyway, so it just is a way for people in industry to know, you know, it is a pattern that is generated from reduced stress in materials.
Thank you. Do they use that for quality control?
Yep.
From our chat, Agent D and Agent J, can you tell us more about your K through 12 outreach at the University of Rochester?
Yeah, of course. So right now it's kind of been usually an outreach that's been organized through SPIE, but it's recently been handed over to kind of us as a way to lead it and make it its own unit, so to speak. So right now what it consists of is several different branches where we have either PhD students that will go to local high schools and talk about the research and kind of redefine the definition of a standard scientist to show that not everyone that is a scientist looks the same, comes from the same background, etc. And there's then another group of students that will essentially just go to different schools as well, similar to the PhD talks, but they're equipped with the demos that we were showing and some more. So the main one that we're currently working on is a total internal reflection kit. And it's essentially talking about what happens when you say shine a laser into a hole in a bucket that's filled with water, and to kind of explain that this is how the internet works. This is how different things can relate to your everyday life, and show it in a fun and interactive demo. So that's kind of the main kind of, I guess I'd say, spiel that we're on so far, is essentially saying these are the things that we're specialized in doing, and this is what we can bring to schools to get people engaged in optics, interested in optics, but also just aware that optics is right here, because it's such a niche field that many people may have seen it every once in a while, but the name of optics pairing to the University of Rochester isn't always a one-to-one. So that's what we're working on. Then if you want to make any additions.
Yeah, so we go to different high schools, or we'll have high schools come here, and then we'll give them lab tours of the labs that we have here. Over the summer, we also help with Photon Camp that has high schoolers come in here and then get some lectures from professors, and then they end up having a poster session at the end. So we have just a lot of different interactions with high schools, and sometimes we'll also go to elementary schools and do some fun demos for them.
So when you go and visit the elementary schools, the younger children, what do you tell them about what they can do from what they learn? Are you already kind of pushing them along to a career in science?
So we kind of just try to get them interested in learning more about what's happening during the demos. So we'll have some demos where we have like different colored balloons, and we'll hold up a laser to them and see which balloons end up popping. And then we'll have other demos where we just like show them cool effects like the rainbow people, so they get to see all the different colors. And then maybe later when they're a little bit more ready to learn about the more complicated parts of the demos, then they'll have an interest and they'll just know that they exist. So they'll have some interest in learning more.
So Wayne asks if the university has participated in the design of science museum exhibit.
We've seen a couple.
Demetrious, the Rochester Museum and Science Center, which is going to be when everybody comes to Color Impact 2025, Monday reception is going to be at that museum, and there is a illumination exhibit, and that was all put together by different companies in Rochester and the University of Rochester. So come to Color Impact. I'm going to give another plug because the Monday reception is going to be at that Museum and Science Center.
And we've also had, during the eclipse recently, we had a table there at the museum, and then we had just a few different demos that we were showing off to people there.
Nice, very nice. So Megan, can stress patterns be used for material identification?
So I would need a little bit of clarification on what is meant by material identification.
Robin, would you like to unmute yourself and ask the question? Robin's going to ask it.
Can you tell the difference between different types of plastics, for instance?
So in my thinking, the stress patterns would be more useful in determining the method that plastic was made. If you wanted to compare different plastics, you would probably want to either use chemical methods or compare them based on the refractive index properties rather than stress patterns.
I was thinking of crystal analysis.
With birefringence, Robin?
Yes.
I mean, they do have birefringence meters that you can compare different crystals.
Mm-hmm.
But that's not a topic that polarization would be used for. So
There's another questions up there.
There's another question from Robin about does polarization affect spectral analysis?
it can definitely. So if you need to have non-polarized light sources, that's why in a lot of spectral analysis tools like a fiber optic spectrometer, they have just a non-polarized light source. And they use diffraction in that in order to split the wavelengths. They lit different colors, but you need to start off with an unpolarized source. If you were to polarize, it should be before when the light comes out of the fiber, or you would polarize it in that way. You can see if an optic is coated, you can be able to tell the difference in reflectance and transmission when you alter the polarization.
So related to the outreach program again, is it restricted or localized to the Rochester area, or will you travel to other parts of the country?
So right now it's just local because this is the first semester where we've actually made it an official role. But as a more unified program, the goals that we would have, I've been very ambitious with the ones that I've set just this semester so far. So once everything is kind of at least set in stone, has a little more structure to it, that would be the goal. Because we currently have I guess I'd say a YouTube channel-esque thing that's been going around, but we haven't really used it as much. So that would be the way that we could get it to different countries as well. But yeah, that's what we have so far.
Yeah, we also have had plans in the past to look into getting like 3D printable models of our demos or just parts lists that we can send out to different people and then they can make the demos themselves and then have like a little description to understand what it is and how it works. So then hopefully other people can just find the demo online and then print it out and then look into giving it to their people.
So related to your parts list, Maggie asks, you have tape on your list. What is that for?
So
Maggie, is there a specific agent you want to direct that question to?
No, I just know we have lots of fun playing with tape and polarization. So I wanted you to share why the tape's on there.
Yeah, so when you place the tape down on the polarizer, it will sort of all be one really pretty color. And so you can actually layer the different tape and make almost little artworks with them. And then as you rotate the polarizer, the color changes and it gives this really cool effect. And it's especially something that's really good for children because, I mean, kids, they'll just get excited by being able to stick tape on stuff. But then when they can hold the polarizer and then move it around and see the thing that they made being these really pretty colors. So that's another really cool item for the polarization demo.
Yeah, good. Yeah. We have them cut up all kinds of plastic containers and put tape on them. So that's fun.
Mm-hmm.
So,
So there's
Agent D.
one question here.
Yeah,
Sorry, to all the speakers, what's the difference? What difference do you think it makes for younger students and for everyone to learn more about how we see optics?
So I think I'm sure everyone's going to have a different answer, but for me, I came into U of R not knowing much about optics. And then I was just very surprised by how sort of ever present it is in our world. Like one thing a professor said one time was they just held up their phone and they said, "This is optics. The screen, the wavelengths of the lights on the screen. There's 2 cameras. Now the cameras can do, like they can measure things. There's IR sensor that does your facial recognition. When you go and use the bathroom and you want to wash your hands off and you use the automatic paper towel dispenser, that's using optics, that's using lasers, cameras. Every way that we see the world, colors, like it's sort of ever present. And in a lot of fields, it is a vehicle for performing measurements. Particularly, it's really great because it's non-invasive. Like if you want to chemically test something, you're gonna have to pick apart that sample, whereas with optics, if you know enough about sort of your experimental setup, you're able to determine a lot of things without ever actually touching it. So I guess for me, it's really interesting to see this behind the scenes kind of view of all these different areas of science you can dip your toes into with optics because of the methods that it opens up. So
I guess I could say the importance of showing the demos around as well is like just to get people aware of what optics is. So like I was saying before, that many people really haven't heard of it before, and myself included. When I was a high schooler, I had no idea that there was, I really didn't even know that University of Rochester was a thing as a junior in high school. I live 15 minutes away from the school, never knew it existed until I happened to take an optics class in high school. And my first thought was, oh, yeah, I like lasers. I like shining them around. Sure, I'll take an optics class. And it ended up being so much more than I actually would have ever thought of like, oh yeah, this is literally like Megan was saying, it's everywhere. It's what you see and interact with constantly, not just a laser or not just glasses. It's not just one thing. So to have all these different experiments to show kids is like, you may not like this area of optics. You may not even know what optics is, but you don't have to just choose one thing. You can really do whatever you want and whatever you find interesting. So that's what's really motivated the things that we're doing here.
Yeah, optics in general is just really good for getting kids interested in the world around them. Really, everything that we see, or I mean, even things that we don't see, are involved in optics. There were people mentioning in the chat that fishing, you can use polarized sunglasses to see the fish in the water clear. There's farming where we use image sensors to find weeds and then we can get rid of them. Really, just everything that we do has some amount of optics in it. And then just getting kids to know like they have an option of studying optics, or to know that whatever they have questions for, it's good to ask, because really any question they could ask could have optics involved. And there's just a lot of different aspects of every field that involves it.
Thank you.
Lena, you have another question to ask?
Yes, there's a question about some current special screens. We can see 3D perception without any polarized glasses. What's the main idea or difference on those screens?
Does Ibrahim want to unmute and clarify his question a bit?
Like,
Yeah, here he goes.
Hey, of
I
course.
think it was.
Yeah.
Okay.
Hey, yeah. Hey, guys. They were really very nice and then very practical information. I really like your presentations. But my question is like about like I saw some screens and when I look at them and then they claim that they kind of 3D. Yeah, I got some perception, but I don't know the idea. Like without like naked eye, when you look at the screen, you see some 3D effects on that movie or like video. But what is the technology behind or the technique? Or have you ever seen this one?
I know there's a more modern technique that I don't think is as like becoming as widespread yet, but I know it's sort of at the forefront of using eye tracking to actually directly project an image into either one of your eyes. But I don't get the impression that that's at the point where it's regularly or like commonly going to be available. So
I guess I would want to ask a clarifying question to see, is it like, say you're looking at just one computer screen and then you're seeing the depth in different parts of the screen, or?
Yeah, it is. Actually, like they say like we should like certain angle to the screen. Therefore, like we can feel that perception. Like if you sit, for example, like that, you can see that perception. But if you like sit in a certain direction angle, you can see that perception. But as I said, without any special equipment, just the screens and then do it.
Yeah,
Like,
so my,
yeah. Yeah, like
What
if it's like something not familiar, it's okay then.
yeah,
So
so
I
the
wanna-
first,
Go ahead.
so the first thing that comes to mind would actually be the polarizers that are on the screen. So you can have a similar thing with, say, a computer at a bank, where
Mhm.
if you have the screen just sitting here and you look at it from different angles, if you sweep
Yeah, you
through
can
that,
see
you
it.
can't see the screen versus you can. So I'm wondering if it's a similar aspect of that, whereas if you look at the screen from a different angle, you're getting a different polarization to your eye, so it could have more depth than another one. So that would be the first thing that popped to mind for me.
Yeah, that makes sense. Yeah. Okay.
I-
Thank you so much
I-
and happy. Yeah. Sure.
I appreciate everybody's attention, and I want to ask the last question to Dr. K. She kind of
so
quickly went
much.
over the fact that she's going to, by the time we get to Rochester next year for the conference, she'll be the president of the organization. So I want to go ahead and remind you that we are going to have Color Impact 2025 in Rochester next year. And if you want to know more about what these students are talking about, but Jennifer, can you tell us why you think that the optics program is growing so fast?
Well, because we are offering a new remote master's degree. And also undergraduates, when they come to the University of Rochester, they don't know about optics. And so we have students like Megan and Demetrious and Jayvyn, they will go out when it's move-in day for freshmen, and they will offer them, if it's a hot day, they'll offer them an ice cream sandwich, and they'll talk to their parents about how optics is an enabling technology. It will enables technologies, and that you can get a really good job when you graduate. So that's another reason that our undergraduate program is growing. But with the master's program, we just have different flavors of the way to get a master's degree. Our PhD program is growing because our faculty is growing. So we have more faculty now at the Institute of Optics, and with each new faculty member, they need to have a group. And so we will be admitting more PhD students as our faculty grows. So that's the Reader's Digest version.
Thank you. Okay, Lena, the screen is yours.
Well, on behalf of the ISCC, I want to thank you for your wonderful presentation and to all our speakers, and for sharing that inspiring work. Our next Fluorescent Friday event will be in the spring. We encourage you to sign up for newsletter or become a member of the Color Council to find out which university will be illuminated in the Fluorescent Friday spotlight. So stay tuned, and thanks everyone for joining us today, and have a great Fluorescent Friday.